A container is running. Inside it sits a file you actually care about, a customer upload, a database page, last night's logs. Then someone types a single command and the container is gone. The process dies, the writable layer evaporates, and the file, if you never planned for this moment, the file dies with it. That is the quiet disaster Docker was designed to make easy. Containers are meant to be disposable. You replace them the way you replace a light bulb. Unscrew the old one, screw in a new one, keep going. The trouble starts when the bulb is also the filing cabinet. Stateless web servers can live this way. A database cannot. Configuration cannot. User photos cannot. Anything that must still exist after the application is torn down is now at war with the very idea of a container. So the question that opens this story is not a feature list. It is a stake. What survives when the application does not? How do you keep software replaceable without making memory optional? The rest of this film is the answer operators had to invent. A storage layer that outlives the process, can be shared without copying, and still stays out of the host's most dangerous directories. The name of that layer is a volume. But before we trust it, we have to feel why the default file system was never enough. Every container has a writable layer. Think of it as a scratch pad glued to the image. The image itself is read-only. Anything the process creates, a file, a folder, a lock, a cache, lands on that pad. Here is the part that matters. When the container is destroyed, Docker throws the pad away. Persistence beyond containers is not the default. It is a special arrangement. That arrangement is useful. You can experiment, crash, rebuild, and never leave junk behind. For a microservice that only talks over the network, vanishing is a feature. For anything that stores state, vanishing is a betrayal. The sources put this in blunt terms. When a container is destroyed, its writable layer is also deleted. Data stored in a volume remains intact. The volume is not a nicer folder. It is a different life cycle. The container can die. The volume does not have to. Imagine a hotel room. Guests come and go. The mattress stays. If you treated the mattress like the guest, throwing it out with every checkout, you would never keep a reservation book. That is the writable layer without a volume. So the first design decision is a split. Application logic stays ephemeral. Valuable data is asked to live somewhere else. Somewhere Docker can still see, but the container cannot accidentally take with it to the grave. There is a second disaster, quieter than deletion: isolation. Modern systems often run the same service more than once. 3 replicas of an API, 2 workers reading the same configuration, a front end and a back end that both need one shared file. If each replica copies that file into its own writable layer, 2 things go wrong. First, you waste space. The same bytes live in every image and every container. Second, the copies drift. Someone edits replica 1. Replica 2 still has yesterday. You no longer have a file, you have a rumor. Copying data into every container is how teams accidentally invent 3 sources of truth. Isolated services are easy to replace, but files created inside them cannot stay synchronized unless they are not really inside them. That is the sharing problem. You want isolation of processes, not isolation of the one document those processes must agree on. A volume answers both stakes at once. It persists beyond a single container, and it can be mounted into several containers at the same time. One storage object, many readers and writers, no photocopier. The picture is almost architectural, several isolated boxes, and one bar of storage they all lean on. The boxes can be replaced, the bar stays. The next chapter is what that bar actually is, and why it is not just a folder on your laptop. A Docker volume is storage that Docker manages for you, kept in a reserved part of the host file system. On Linux, that neighborhood is typically under var lib Docker volumes. Non-Docker processes are not supposed to wander in and rearrange the furniture. From inside the container, the volume looks ordinary. It appears as a directory or sometimes a single file. The data looks the same no matter which mount mode you chose. The difference is ownership and fate, not the view. Volumes are, in this account, the most effective way to store data for containers. You can create one yourself with Docker volume create. or Docker can create one for you when a container or a service starts and asks for a mount that does not yet exist. The decoupling is the point. The volume has an independent life cycle. No container has to be running for the volume to exist. Unused volumes are not automatically deleted. They wait. If you want them gone, you prune them on purpose. That patience is both a gift and a mess. Data survives accidents. Disks fill with forgotten names. We will come back to that cost. For now, hold the definition. A volume is Docker-managed storage whose life is not tied to the process that first used it, and whose contents can be shared without being copied into every image. The software can remain a light bulb. The filing cabinet finally has its own address. Picture one node in the middle, call it the volume. Around it, several containers, not stacked, not nested, just attached by mounts, like ships tied to the same pier. Each container still has its own writable layer for throwaway files, but the important path, /data or /shared-volume, or the database directory, is not on that layer. It is a doorway into the pier. Shared access is not a metaphor. A volume can be mounted into multiple containers at the same time. Different applications, different services, one body of bytes. If one container writes a file, the others can see it, provided they mounted the same volume at a path they understand. This is how you stop the rumor problem. There is only one copy that matters. Replicas do not each keep a private edition. It is also how replacement becomes safe. Destroy container A, start container B with the same volume name and the same destination path. The new process walks through the same doorway. The furniture is still there. Volume cleanup is deliberately conservative. Even if no container is currently using a volume, it remains available. Docker will not quietly throw away the pier because the ship sailed. You free space with Docker volume prune, and only then. The architecture is simple on purpose. One managed store, many temporary clients, independent lives. The next tension is that this is not the only way to attach storage, and the rival designs have very different personalities. Two ideas compete for the same job. Put host storage into a container. One is the bind mount, the other is the Docker volume. They look similar from inside the process. They are not similar as systems. Storage location. A bind mount can be any user-specified directory on the host, your home folder, a project tree, even a sensitive system path. A volume lives where Docker puts it, in a specific storage area. Management. Bind mounts are manual. They depend on the host file system existing, being permissioned, and staying put. Volumes are automatic. You talk to them through the Docker command line or API. Lifecycle. A bind mount is tied to the host's directory structure. If that path moves or the machine's layout changes, the contract breaks. A volume's lifecycle is independent of the container and less entangled with how a human organized their disk. Performance. Bind mounts can be fast, but they vary by host operating system. Volumes are described as optimized, generally better input and output in production. Primary use. Bind mounts shine in development, syncing source code so you can edit on the host and test in the container in real time. Volumes are the production choice for databases, stateful apps, and data that must persist. Security and isolation. Bind mounts score low. A container can modify sensitive host files if you pointed it at the wrong place. Volumes score high. They are isolated from the host's most sensitive system files. The rivalry is not good versus evil. It is workshop versus vault. You want the workshop when you are writing code. You want the vault when the bytes are a customer's database. Mixing them up is how a convenient path becomes an incident. Docker does not offer one mount. It offers a small family, and they all look like folders from inside the container. Volumes we already met. Docker manages them on the host, typically under that reserved volumes directory. Non-Docker processes should not edit that area. You create them with Docker volume create, or let Docker create them on demand. Bind mounts we also met. They can live anywhere on the host. Crucial system folders can be bound. Non-Docker processes can always modify them. Compared with volumes, they are less useful as a general persistence tool, more of a development clamp. Then there are named pipes. A named pipe mount is for communication between a container and the Docker host. The typical use is connecting to the Docker Engine API from a third-party program running inside a container. It is a hallway, not a warehouse. And then TMPFS. These mounts live only in the host's RAM. They are never written to disk. They look like a normal folder inside the container, but the data is volatile. Stop the container and it is gone instantly. That makes TMPFS perfect for security tokens or high-speed scratch files you do not want lingering on a platter. So the family has 4 personalities. The volume wants to survive. The bind mount wants to share your actual laptop tree. The named pipe wants a conversation with the engine. The TMPFS mount wants to forget. Choosing among them is not a style preference. It is a statement about whether the data should outlive the process, touch the host, talk to the daemon, or vanish when the lights go out. Even inside the volume family, there is a fork, named versus anonymous. A named volume gets a custom human-readable name, myvol.demovolume, MongoVol. You can track it, back it up, remove it on purpose, and point many containers at the same name. It is built for long-term data, databases, configuration, anything you will still care about next week. An anonymous volume gets a random, long alphanumeric identity, no nickname, hard to track, easy to lose in a list. Reusing it means hunting the specific identifier, which is impractical. These suit temporary storage or a bit of state isolation you do not intend to curate. Here is the cleanup twist. Anonymous volumes are deleted automatically if the container is run with the remove flag, the flag that says, when this container exits, erase it. Named volumes persist until you explicitly delete them. That is why anonymous volumes become clutter. You experiment, you forget the identifier, the disk quietly fills with volumes that have no story attached. Named volumes are how you refuse that fog. The operational rule is almost moral. If the data has a name in your head, give it a name in Docker. If it does not deserve a name, do not be surprised when nobody can find it, or when a prune finally does. Control begins with 3 verbs: list, create, inspect. To see what already exists, you list volumes. The command is docker volume ls. On some systems, people prefix it with sudo. The output is a roster, driver, name, the thin census of everything Docker is currently babysitting. To make a new one, you create docker volume create, then the name. You can attach labels at birth. One example sets a description and a version. Description myvol, version 1.0.1, and names the volume myvol. Labels are not decoration. They are how a future human or a future script knows why this lump of disk exists. Inspect is the close-up. Docker volume inspect, then the name. You get structured detail, where it actually lives on the host, which driver owns it, what labels you stuck on it, mount point, options. This is the moment a volume stops being a slogan and becomes an object you can audit. Naming and labeling are the unglamorous half of persistence. A durable store you cannot identify is just a slower way to lose data. The sources insist on proper naming and labeling conventions when you establish volumes. Treat the name like a caption on a museum piece, not like a temporary file name. Once the object exists, the next question is the doorway. How does a running container actually see it? The classic doorway is the short flag, -v, or the longer twin, --volume. They accept a host-side volume name and a path inside the container, separated by a colon. Read it left to right, volume name, colon, path inside the container. That is the whole contract in one token. One documented pattern starts an interactive container from BusyBox and maps volume name to /data. Another starts Ubuntu, names the container, and maps a named volume onto /shared-volume. Same grammar, different images, different interior paths. You can also pass a volume driver. --volume-driver tells Docker which plugin or backend should own the storage. Combined with --volume, that is how a container is granted access to a volume that is not just the local default. There is a second, more explicit doorway we will meet later, --mount, with labeled keys instead of a colon sandwich. For now, memorize the sandwich. It is how most people first attach persistence. After the container starts, you are inside a shell. change directory to the mount path, list files, write something. That write does not land on the disposable pad. It lands on the peer. Exit the container. The peer does not exit with you. The experiment that proves it needs two containers, not one. Writing is not persistence. Reading from a different life is. Here is the experiment. The sources walk like a lab procedure. Start the first container. Mount the named volume at /shared-volume. Give the container a name so you can talk about it. You land in a shell. List the directory. Change into the shared path. Echo a line of text into a new file. List again. The file is there. Exit. The first life is over. If volumes were a myth, that file would now be folklore. Start a second container. Different name, same image family. Same -v mapping, the same volume name, the same path inside. Walk into /shared-volume. List the files. The file is there. The contents match. Not a copy you packed into the image, the same volume mounted again. This is the payoff the whole architecture was aiming at. Isolated processes, one memory. The second container did not need the first container to still be running. It needed the volume to still exist and the mount line to point at it. That is also why the colon grammar matters. Get the volume name wrong and you have attached a different peer. Maybe a brand new empty one Docker helpfully created. Get the path wrong and you are staring at a different room. The experiment only works when both lives agree on the name of the storage and the place they will look. Two containers, one file. That is the smallest possible proof that replacement can be safe. A second demonstration uses a different volume name and a blunter payload. Run an interactive Ubuntu container with -v mapping demo volume to /data. Inside, write the word foobar into /data/foo, then cat the file. The shell prints foobar. Ordinary. Almost boring. Now the interesting half. Launch another container that mounts the same demo volume. Read the same path. The word is still there. Nothing mystical happened. The first process opened a file on a mount that was not the writable layer. The second process opened the same mount. The bytes never belong to either container. They belong to the volume. You can feel why this matters for a database. A database is just a very serious version of foobar. Many files, careful locking, the same rule. Point the official data directory at a named volume. Kill the database container. Start a new one with the same volume on the same path. The pages are waiting. Content population follows the same idea. Docker can seed a volume from image contents when a volume is first used, depending on how you mount it. Another container can then inherit those volumes with a flag we will reach shortly, volumes from, and treat the populated store as a backup source. The story on screen is always this small. Write, destroy or leave, reconnect, read. If that loop works, stateful services are allowed to live in a world of disposable processes. If it fails, you are back to the light bulb that was also the filing cabinet. Survival has a cost, and the cost has a command. Docker volume rm, then the volume name or identifier. That command permanently deletes the stored data. The sources are not gentle about this. Before you remove a volume, take a backup. There is no recycle bin with a sentimental policy. A volume generally cannot be removed while a container is still using it. You stop or remove the dependent containers first. Persistence is not a lock against your own cleanup. It is a lock against accidental container deletion. Your own RM is still sovereign. That is the other half of the independent lifecycle. Docker will not prune a volume just because the last ship left. You must say the words, and when you say them, the peer is gone. This is why naming matters again. Removing the wrong anonymous identifier is easy if you cannot tell volumes apart. Removing my vol when you meant an old experiment is a human error with permanent physics. Think of RM as the opposite of the opening disaster. The opening disaster was data dying because a container died. This command is data dying because you asked it to. Both are irreversible, only one is supposed to be. The operational discipline is simple and easy to skip at 2 a.m. List, inspect, backup, then remove. The volume that made replacement safe can still be murdered on purpose. Treat that power like a fire alarm, not like a broom. Now raise the stakes from a text file to a database. The documented pattern starts Mongo in the background. Give the container a name. Map a named volume, Mongo vol, onto /data/db. That path is where Mongo keeps its files. Two environment variables set an initial root username and password. Read the mount again. Volume name, path inside the container. Mongo vol is the durable object. /data/db is the room Mongo already knows how to use. You did not invent a new database feature. You pointed the existing one at the peer. This is the production use case the comparison table was aiming at. Databases, stateful apps, persistent data. If the Mongo container is removed, the volume remains. Start a new container with the same mapping and the data directory is still populated. You can verify without romance. After Mongo has written, run a short-lived busybox that mounts the same volume and lists /data/db. The files are visible to a completely different image. The database engine is not the owner of the bytes, the volume is. Environment variables in that run command are just configuration for the process, credentials the developers chose. They are not the persistence mechanism. People sometimes confuse settings with storage. Settings tell the program who it is. The volume tells the program where memory lives. A replaceable database container is the original question, answered in one line of mount syntax. The light bulb can be swapped. The reservation book stays on the desk. One-off run commands are how you learn. Compose is how a team writes the same idea down so it happens the same way every time. In a compose file, services are the containers. Under a service, you list volumes as mappings. The example uses Mongo vol mapped to /data/db, the same pair we just used on the command line. At the bottom of the file, a top-level volumes key declares Mongo vol. That declaration tells Compose this is a named volume it should create and manage, not a mystery path. The sources also show a front-end service based on a Node long-term support image, mounting that same named volume. The names in the example are a little mixed. A Node image with a database path, but the mechanism is what we need. A named volume can be referenced from the service that needs it, and defined once so Compose knows it is real. This is documentation as architecture. Instead of hoping every engineer remembers the -v line, the file states, this service has persistent data, and this is the volume's name. Sharing follows. Multiple services can mount the same declared volume if that is what you intend. Isolation of processes, unity of store, now in YAML instead of a remembered command. Compose does not change the physics. It changes the odds that the physics will be applied on the next deploy. The volume still outlives a container. The file just makes that intention visible. Two spellings, one job, different tempers. -v is concise. It is appropriate for basic named volume or bind mount usage. Mongo vol, /data/db. Fast to type, easy to misread. The order of fields is a folklore you have to remember. --mount is explicit. It uses keyed fields. Source equals the volume name. Destination equals the path in the container. You can see which word means what without reciting a rhyme. The longer form also carries more options. Volume drivers, read-only mode, propagation, labels, permissions. When the mount is no longer a simple name-to-path pair, the short flag starts to feel like a packed suitcase. The long flag is a labeled crate. There is no moral victory for verbosity. Use the short flag when the story is simple. Use the long flag when you need to say driver, readout only, or a destination without hoping the colons fall in the right places. The sources prefer the explicit form for complex mounts. That preference is about accidents. A swapped field in a colon list can bind a host path you did not mean, or create an anonymous volume you will never find. Keyed fields fail more loudly and more honestly. Think of -v as a note on a napkin and --mount as the same order written on a work ticket. Both can get you lunch. Only one belongs in a production runbook. Persistence without permission is just a longer incident. In a Docker file, you can prepare the directory a volume will use. Make the folder, change its owner to a numeric user and group. One example uses 1000, change the mode to 755, then declare volume at that path. The point is to preserve security and integrity before any container writes a byte. Mounting read-only is the other lock. Add the suffix :ro on a -v mount, and the container can read but cannot persist changes through that path. The long form can set read-ODI as a field. Configuration that must be seen but not rewritten belongs here. A compromised process can still try. The mount refuses. This is how you split trust. Some volumes are desks, some are display cases. A database data directory is a desk. A bundled configuration tree might be a display case. Usage monitoring sits beside permission. Knowing that a volume exists is not the same as knowing it is filling the disk or that the wrong user owns every file inside it. Inspect, list, and ordinary tools that look at the mount point are how you keep persistence from becoming a silent leak. The story tension tightens. We made data survive container death. Now we have to stop the wrong process from rewriting it, and stop the right process from running as a god. Survival is not the same as safety. The next tools are about inheriting volumes and watching them. Sometimes you do not want to restate every mount. You want to say, take whatever that other container already has. The flag is volumes from. Start a new container, give it a name like backup, and point volumes from at an existing container. The newcomer inherits all of that container's volumes. This is a practical backup pattern. The original process keeps running, or at least keeps its mounts defined. The second process is a specialist. Archive, copy, inspect. Walking the same peers without you retyping each name and path. Content population pairs with this. A first container can fill a volume from image contents or from its own rights. Later containers, whether they remount by name or inherit with volumes from, see the populated store. There is a discipline here. Inheritance is powerful and a little opaque. If you do not inspect the source container, you may pull more volumes than you intended. Named mounts you declare yourself are easier to reason about. Volumes from is the shortcut when the set of mounts is the point, especially a backup of everything a service touches. Together with the write and reconnect experiment, this is the operational toolkit. Create, mount, populate, share, inherit, read. The architecture is no longer a diagram. It is a sequence you can run. So far, the peer has been on one host. Real systems outgrow one host. Docker Engine volume plugins link an engine to external storage systems. The sources name Amazon EBS as the kind of place data should be able to live. The point is survival beyond the lifespan of a single Docker host. If the machine dies, the volume idea should not die with the machine. You create such a volume by naming a driver. One example, Docker volume create. Driver equals Flocker, then the volume name. Then you run a container with -- volume mapping that name to /data. The plugin protocol is a handshake. If a plugin registers as a volume driver, it must give the Docker daemon writable paths on the host file system. The daemon then bind mounts those paths into containers. The plugin's job is to make sure those paths are the local face of something larger, a remote disk, a replicated store, a cloud volume. The JSON sketch is almost shy. A name, a bag of options. Behind that small object can sit an entire storage product. This is where volumes stop being a local convenience and become a contract with infrastructure. The container still sees a directory. The operator now has to care about the driver, the options, and what happens when the host is not the center of the universe. The unresolved pressure appears. Persistence on one laptop is a solved demo. Persistence across machines is a negotiation. Cross-machine sharing makes the negotiation concrete. Volume drivers let the same named volume idea point at remote storage. The compose example declares a volume whose driver options set type to NFS. NFS, a network file system, means the files live on a server and clients mount them over the network. Containers on different machines can, in principle, see the same tree. The documented sketch is minimal. It specifies the type. A complete setup would also name the server, the export, the mount options. The sources describe an architecture that separates an NFS server from an NFS client. One side holds the bytes. The other side runs the application containers that consume them. This is the replica problem at building scale. Not 3 containers on one engine sharing a local volume, but services on different hosts that still must not drift. Copying files into every machine would recreate the rumor problem across a network. A driver-backed volume is an attempt to keep one truth. S3-style object stores and NFS are mentioned as the sort of remote backends teams reach for. The exact product matters less than the shift in responsibility. Docker is no longer hiding a folder under its own directory. It is attaching a network service and calling it a volume. Latency, permissions, and failure modes all change when the peer is on another floor of the building. The command line stays almost polite. The physics do not. That politeness is useful. It is also how people forget they now depend on a network. Independent Lifecycle has a junk drawer. Because unused volumes are not deleted automatically, a busy machine accumulates them. Experiments, abandoned database names, anonymous identifiers nobody can map to a ticket. The store that saved you from container deletion will happily hoard forgotten worlds. Inspect is how you identify a suspect. Docker volume inspect, then the name. Read the mount point. Read the labels you hope you added. Decide whether this object is a museum piece or landfill. Remove is how you delete one. Prune is how you delete the unused crowd. Docker volume prune removes volumes not used by at least one container. It is a broom with a wide head. Useful. Dangerous if you have a volume you still care about that merely has no container attached right now. That last sentence is the trap. A backup volume with no running container looks unused. A volume you plan to attach next week looks unused. Prune does not know your calendar. It knows attachments. The hygiene ritual is therefore not prune often as a slogan. It is name what you keep, label why you keep it, detach only when you mean it, backup before RM, and prune when you have checked the list. Storage clutter is the unresolved operational tension the sources leave on the table. Persistence helps, judgment still has to show up. The next chapter is where judgment meets platforms that do not share your assumptions about permissions. When the demo works on one laptop and fails on another, the volume is rarely haunted. The platform is. Permissions are the first suspect. A process inside the container runs as a user. The files on the volume have owners and modes. If you did not chown the directory in the image, that 1000 example, the process may not be allowed to write the very store you created to save it. The volume is fine, the door is locked. Virtualization adds another layer. Docker on a desktop often sits above a hidden Linux virtual machine. Paths, performance, and file watching behave like a guest, because they are a guest. Bind mounts that feel instant on native Linux can stutter. Volumes managed inside Docker's area often behave more predictably, which is one reason the comparison table favored them for production I/O. Windows has a specific caveat. Shared Windows volumes through Docker Desktop get default read, write, and execute permissions of 0777. Those permissions cannot be customized. If an application requires a stricter or different mode, host-mounted volumes on Windows will fight you. The advice is to use non-host-mounted volumes or change the application to accept those defaults. Shared volume permission issues also appear when two containers run as different users and both write the same tree. The second writer inherits the first writer's ownership choices. Isolation of processes does not automatically isolate identities on the files. Troubleshooting is therefore a story, not a reboot. Who owns the path? Which mount type you used, which operating system is pretending to be which, whether you needed a vault and accidentally used a workshop. The volume did its job. The surrounding world still has opinions. We opened on a vanishing container and a file that had no right to disappear. The answer was not to make containers permanent. That would betray the whole point of replaceable software. The answer was to split the lives. Let the process be a light bulb. Give the data a peer. Volumes are that peer. Docker managed, independently alive, shareable without photocopying, generally safer and more production ready than a bind mount into whatever folder happened to be handy. TMPFS exists for secrets that should die with the process. Named volumes exist so humans can find what they stored. Plugins and network drivers exist so the peer can stand on another host. The proof was small and sufficient. One container wrote, another container read. A database pointed /data/db at a name. Compose wrote the name down. Read-only mounts and Docker file permissions tried to keep survival from becoming vandalism. Prune and RM reminded us that permanence is a choice, not a law. What this knowledge made possible is ordinary and enormous. You can throw away a container that is sick, outdated, or simply unfashionable and keep the customer data. You can run two services against one file without inventing two truths. You can treat infrastructure like cattle and still treat records like something with a name. The field is still chasing the harder half. Which backend, which permissions, which driver, which team convention keeps persistent data clean across hosts, platforms, and people who will not be in the room next year? The container can vanish. The question that remains is whether we will still recognize the volume when we need it.